Hello? Can you hear me? Can you hear me? Anybody? No, you can't hear me? Okay, okay, discrete math and probability, that's what we're teaching you. Why are we teaching this to computer scientists? Okay, I can't talk anymore after that. I think I injured my voice. All right, it's by this guy. I had nothing to do with it. I don't think I sound like that, for the record. I think he doctored my voice, but that's fine. Okay, very impressive piece of engineering. Okay. All right. So, can you hear me? Yeah. 3-packet message. I say it's a satellite, so these things are not completely reliable. So say the satellite is talking to your GPS device. What? Did somebody ask me a question? How tall am I? I'm 6'2". I'm shrinking though. Okay, so I don't know where that came from. So there's a 3-packet message. We want to send 3 packets, right? It tells you somehow those 3 packets have some information that the satellite wants to tell the GPS device. And so it's a long way, so you lose some messages. So there might be 6, you want to send more because you might lose some of the packets. Okay? So what's the right thing to do? Maybe you're willing to send twice as much. And so we'll send 2 copies of each packet. What's the problem with this? Well, here, I'm going to lose 3. Say I lose 3, which would be great if I lost the right 3, but you see the problem here? We got packets 1, 1, and 3, but we didn't get packets 2. So we don't know what's in packet 2. Right? Okay. So this is the problem. Right? We should have a solution. Right? We should have a solution. Okay. So let's get a solution. Okay. End packet message. The framework is there's an end packet message that loses in a channel. The channel is something you send it over, maybe a wire here in this case, in this example is the air, that loses some number of packets. We're just guaranteed it loses at most this many packets. So clearly, if you have n packets, you better send n plus k. If it loses k packets, you're going to lose information. That's both intuitively, and you can do a simple calculation and see that has to happen. Okay? And so now you want to say any n packets should allow the reconstruction of an n packet message. Any n packets. Right? Did you see where that wasn't true in the previous case? If we just made 2 copies of every packet, if we lose both copies of one packet, we're done. Even if we get all the other packets. Okay? So there's a thing that we've seen before. Okay? Any endpoint values allow the reconstruction of a degree n minus 1 polynomial. Okay? Now that's a mouthful, but it really isn't. There's another form of this that you've learned many, many times. And what is that form? What's a line? It's a linear polynomial, degree 1 polynomial. And what determines a line? 2 points. 2 points determine a line. Does it matter which 2 points? Any 2 points on the line determine the line. Is that clear? Does that make sense? That's today's lecture. Okay? There's going to be a lot more stuff that happens, but really that's all there is to it. 2 points determine a line. Those calculations, remember this, given 2 points, you could figure out the slope, you could figure out the intercept. Remember all this? Who remembers this? Okay. Okay, so you should raise your hand because it's very important you remember this. So 2 points, right? You can that's it. Okay, so all the rest, the calculations are the same. There's some level of algebra that we do. This algebra is generalized just a little bit. Yeah. What? No, we haven't. This is we're doing polynomials. But we can skip it if you know it. That's fine. You're cool with us doing? Yeah. It's good to remind me, though. I could miss a whole lecture, but it's possible. But I think I got this. Okay. If you didn't hear, they accused me of not being able to do my job at all. So, what were your names again? Okay. I know what you think of me now. Okay, any to allow the reconstruction. So this is the idea, and I'm going to prove this. Okay? So the idea is that, people are much happier after the midterm, sort of. Okay, sort of. At least they're relieved it's not coming. So any endpoint values allow the okay. So this is the idea. Okay? That's awesome. It's really awesome. Really, 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 really awesome. All right? Any endpoint values, right? That means you just need to send more points on the polynomial. That's the whole lecture. And now I'm going to talk for an hour and a half more. Okay? If all it means that you need to do, now you know what to do. If this fact is true, if any endpoint values allow reconstruction of a degree n minus 1 polynomial, all you need to do is send me n plus k points on the polynomial. When I get them, doesn't matter which ones I have, I can reconstruct the polynomial. That's the idea. That's the idea at the beginning, the idea at the middle, and the idea at the end. Okay? Use polynomials. Okay? So, want to send a message with n packets. You have a lossy channel. You lose k packets. Can you send n plus k packets and recover the message? Degree n minus 1 polynomial is determined by any n points. So, here's a erasure. Did I do the wrong lecture? I did. No, I didn't. No, I didn't. This is the right lecture. Wait a second. Okay, wait. It's the right lecture. Never mind. Oh. This used to be more funny before Kavanaugh, but I had a student review once, and the review was apparently, comma, Satish likes beer, period. Perhaps, comma, he should like it less. And there may be, okay, so that was a student review. Okay, so, where is this? Am I like at the end? What's going on? Oh, you know what? I know what's going on. Yeah, sorry. Okay. There's a LaTeX error. It's a LaTeX error. Wait, okay. Oh, much better. Okay, so it was the idea at the beginning and the middle and the end, because that was the end. Okay, sorry. Okay. Only 400 pieces in this slide. Okay. All right, now it's fine. Okay, wow. Okay, so today, what are we going to do? You're right. Okay, we're going to do secret sharing. Why are we doing this? The other example is much better. So, any k minus 1 know nothing. Okay, this is what we're going to do. Any k knows the secret, right? I was working on these slides just before. I'm a little bit confused why I got, okay. That's why parts are commenting out. It takes a long time to compile. Minimizes the storage, okay? The idea that 2 points make a line, right? That's the idea. Okay. Lots of lines go through 1 point. Okay, so here's a polynomial. Okay, so this is a polynomial, right? So the idea in a polynomial that's confusing for students is x. Okay? X is nothing. It doesn't really tell you any information. It's a placeholder. Okay? So what's specifying the polynomial is the degree and the coefficients. Okay, once you have the coefficients, you know the whole polynomial, right? Okay, so now x is just something you plug in, but a polynomial is an object, right? It's just an object, and it's an object specified for a line. It's a point and a slope. Okay, so it's specified by coefficients, AD through A0. P of x contains point AB if B equals P of A, right? Does that make sense? You can maybe it makes more sense if you think of it as x and y. X is equal to P of x. I mean, y is equal to P of x. Okay, B equals P of A. Okay, that's what it means to contain a point. You remember this notion of locus? A circle is a set of points that are distance 1 from the origin. The points on a line are the ones that satisfy that equation. Okay? Okay. So, polynomials over reals, you know about them. You've used them. Probably more you've used polynomials over rationals, but same idea. And polynomials with arithmetic modulo p. So we're going to do the same thing as we've been doing, as you have done with polynomials, only we're not going to work over the reals or the rationals. We're going to work mod p, because we have all these nice properties in mod p. So we have this notion that it's a field. It's a set of elements with addition and multiplication operations and inverses. And, they call this a Galois field, but if you see a GFP, don't get scared. It's just modular arithmetic. You've already seen it a lot, and that's all we're ever going to use. Okay? We have a set of items, an addition operation, a multiplication operation, and all of them have inverses. Okay? So now here's a polynomial, right? So there's 2 points. It's a line, right? So it's specified here. The line is specified by the 0.5 and 0. Here's a line. It's specified by -1 and 3. There's another polynomial. It has 3 coefficients. It's degree 2, so there's always this off by 1. Something's always a -1 here because it's degree 2, but there's 3 coefficients. It's just 0 indexed. So usually a sub 2 is the coefficient of x squared. But, you've seen it before. Obviously, you've worked a lot with parabolas. That's what a parabola looks like. There's 3 coefficients, right, in the reals or the rationals. And there's another one. It's all good and fun. There's more fun. Polynomials mod p look a little strange. They have no values in between. That's why it's dotted. They only have values at the grid points, right? Because every element, either the input or the output, is an element of 0 through 4 in this or its equivalence class, right? There's no fractions. There's no rationals. Okay, so it's just some sort of thing. You can sort of see the line going up if you let it go. It's just a line, but it wraps sort of. It wraps around, right? It goes like this. Okay, so those are just other polynomials. Here the coefficient is 1. X is just a placeholder. So we can do fun things with lines, right? We can see the intersection point. You see the intersection point, right? But how do we find the intersection point for 2 lines? Well, we say, when does x plus 1, for one line, when you put in x, you get x plus 2. For the other line, when you put in x, you get 3x plus 1. So you want to see when they meet, they should have the same x value, right? And they should have the same y value, right? So this is what this equation says. You set them equal, and then you can solve. You can say this is equal to 2x minus, I'm just doing stuff here. 3x minus x is 2x. 2 minus 1 is 2. And I take the multiplicative inverse of 2, which is 3. Excellent. Then you multiply both sides by 3, and you get x equals 3. Right? So good when the modulus is prime. Okay? Good. Right? So it's just remembering all the stuff. Now you've gone through middle school with modular arithmetic, or right? This is what 2 points, when do they intersect? Right? So now we're going to do this. Okay, exactly 1 degree less than or equal to d polynomial. So it's slightly difficult to parse, but it just says, forget about the less than or equal to. Just say 1 degree d polynomial contains d plus 1 points. Okay? If I give you d plus 1 points, there's only 1 degree d polynomial that goes through them all. Does that make sense? That's the claim. Okay, and less than or equal to is sometimes the leading coefficient may be 0. A sub d might be 0, and that's why it seems like it's less than or equal to. But just think of it as fully general, and then, the less than or equal to is not a big deal. Okay, and again, 2 points specify a line. 3 points specify a parabola. So now we've gone one more, right? We've said, if I give you 3 points, I'm not sure you've ever done this, but it's not hard. It's the exact same thing as a line. Okay? 3 points specify a parabola. So exactly 1 degree d, less than or equal to 1 degree d polynomial with in arithmetic in mod p that contains d plus 1 points. Okay, so we knew that the first fact is for all reals, and it's also true for modular arithmetic. Okay, so let's look, and now we're going to do it in the reals or the rationals, and say, look at those 3 points. What should contain those 3 points? A line or parabola? Oh, look, a parabola. Okay, so how about those 3 points? How about that one? A parabola. Okay? Okay. Okay. Okay, so 2 points isn't enough, right? So now if I do that one, does that determine a parabola? No. And in fact, I can get a lot of parabolas. And in fact, let's say for every value on this axis, on the y-axis, I can find a parabola that goes through it, right? Does that make sense? If I have this point, there's a parabola that goes through it. If I have that point, there's another parabola that goes through it. If I have that point, there's another parabola that goes through it. Okay? So no matter which point I choose on the y-axis, for those 2 points, I can make a parabola go through it. Right? So it's completely undetermined where the y-axis, the y-intercept in some sense, right? Okay. So since I mucked up the lecture, let me tell you back what we're trying to do. Okay. What we're trying to do is we're not trying to do erasure coding. What we're trying to say is that we want to share a secret among n people. I want to hand out some codes to n people, and you guys will know nothing after I hand you the codes. Okay? Nothing. You know nothing. Each one of you can look at it and you know nothing. And I have a secret, and I shared it with you. What does it mean for me to share it with you? If you all got together, then you can figure out the secret. That's what it means, right? I shared it with you, but you don't know it. It's sort of one of these situations where you have 5 guys in the nuclear launch tunnel or something, and you need but you don't want all 5 to have to agree. Maybe 3 of them are good enough. Well, that's a terrible example, but so be it. This lecture has just gone to, well, and so 3 out of 5 are enough, right? So that's what we want. We want that we hand out n, say in that example it's 5, and any 3 of them, any 3 of them, it doesn't matter which one, get together, they can understand what they know the secret. Okay? On the other hand, any 2 of them get together, they know nothing. Not only do they not know the secret, they know nothing about the secret. Not even 1 bit of the answer. Okay? So that's what we want to do. Okay, so now that we see this, okay. So now, where's the secret? Now let's say we use exactly that example. With those 2 points, what should the secret be? The secret is a polynomial. Okay? And I'm going to hand out 5 points on the polynomial. Any 2 of you will look like this. These 2 blue lines. And I'm going to say the secret is a value of the polynomial at 0, which I don't hand out. Okay? So now, with these 2 points, I can get any value I want at 0, right? There is a polynomial that will go through those 3 points. Every single point over here, it doesn't matter what it is, I can get a different polynomial that goes through it. So those 2 points tell me nothing about the value at 0. Okay? So all I need to do is hand out 5 points that none of the points should be at 0. And then any 3 of them will allow me to reconstruct a polynomial, and I'll know where the 0 where the y-intercept is, and I can reveal the secret. Any two of them, I know nothing, right? Okay, so this is what I'm saying here, right? There is, for those 2 points, if I only know 2 points, there's a polynomial that goes through those 2 points in any value. It doesn't matter what the value is on the y-intercept. On the y-intercept. Okay? Okay, so let's see. So there's exactly 1 degree D polynomial with, so we don't want to use rationals or real numbers because they, they just become a mess when you compute with them. So we're going to use modular arithmetic to do this. And we'll see why more. So this is the scheme, right? You choose A0 to be S. What for a polynomial, what is A0? What is the value of what's the point, what is A0? How do you get A0? What do you plug in for X to get A0 out? 0, P of 0, right? P of 0 is our secret. Okay, that's what I was saying. Okay, so A0 is the secret. And then what I do is I pick a bunch of other coefficients, A1 through AK minus 1, completely at random. So uniformly like to be any member of 0 to P minus 1. Okay. Now, I hand out the shares, and I hand them out to 5 people, or whatever number of people. This is n people, right? I can hand out many more than k, because there's maybe many more than n points I could evaluate the polynomial on. And share I is the point I, P of I, mod P. Okay? I just evaluate the polynomial. This P of I means I plug in I in here. Now, I is a number. Since it's a number, I can evaluate this expression and get a number. Right? Does that make sense? That's what P of I means. Okay? Any k shares gives the secret. That's what the modular arithmetic fact here says. The degree of the polynomial here is k minus 1. And it says any d plus 1 or k minus 1 plus 1 points recovers the polynomial. Okay? I can recover the polynomial. At least that's what the fact says. I haven't shown you how. But at least you know how for a line, for degree 1 polynomial. So knowing k points means you only know only one p of x. Okay? It says it's unique. Exactly one, right? That's what I'm using. So I'm using the fact that you can recover a polynomial, and there's a single polynomial that you recover. So now if you recover that polynomial, then you just need to look at this, evaluate that polynomial at 0, or look at this lowest coefficient, A0. And I have my secret back, right? Evaluate P of 0. Now, any k minus 1 shares gives nothing, right? That's what we argued before. Because no matter what point I choose on the y-axis, I can give you a polynomial that goes through that point. Right? Because that's also from the modular arithmetic fact. Because say I have k minus 1 point somewhere, and now I specify a particular point at 0, now I have k points, and that's sufficient to recover a polynomial. Yeah.
In this case, if someone gave you the point 0, P of 0.
No, they can't. They won't give out 0, comma P to 0. Yeah, he's saying, what if I gave out 0, comma P minus P of 0? Well, that would be stupid. I would just be giving one person the secret, right? Right. Don't do that. Yeah, but today I probably would have done that. It's not going too well, but yeah, that's a mistake, right?
Yeah.
Okay, so.
Like the A, k minus 1, I'm knowing all the coefficients in the secret.
If you know all the coefficients, you don't care about the other coefficients, right? They're just there to hide the secret.
Right, but if, let's say your secret wasn't just the last one, it was like...
But it isn't. That's not our scheme, right? This is the scheme. You can do other schemes, but that's not what we're doing. Right? We're doing something that's very specific. He's saying, what if you spread the secret amount out among the coefficients? There's other schemes that do that, but not this one. Okay. Okay, so knowing less than k minus 1 points, any p less than or equal to k minus 1 points, any point value, any evaluation of this polynomial is possible because there is a degree d, a degree k minus 1 polynomial that will hit all the points you already have and P0. Okay? So it's fairly simple, okay? So now, here's an example. Let me show you how to find it. Here's this for a line. So that contains the points 1, 3, and 2, 4, meaning the x value is 1, and the valuation of this polynomial is 3, and the x value is 2, and the valuation of this polynomial is 4. Okay? So P of 1, so I'm going to evaluate this polynomial, but I don't know the coefficients, right? I don't know A0, A1, and A0. I'm trying to figure that out. So I'm going to plug in 1 for that x, and what do I get? Well, I'm plugging in the x for that x, and I get m times 1, right? I'm plugging in a 1, which is equal to m plus b. Okay, that's P of 1. I've used this point. What should it equal? It should equal 3, right? The value of this polynomial at 1 should equal 3, right? So I plug in 1, and I get an equation. I get a linear equation on the coefficients of the polynomial, right? Okay, what am I going to do next? I have one more point, 2. I should do this. Sorry. My animations don't work unless you compile twice. Okay. Yeah. Okay, so this is the equation for 1 and 3, right? That's why they're highlighted in blue this time. Okay, so now we're looking at this 2 and 4. That's another point. Okay, so we plug in 2 into this formula, mx plus b, and what it gives us is not necessarily a number, but it gives us an expression that involves m and b. It's linear in m and b, and then it equals 4, right? Because 4 is the value that thing should evaluate to. Now, do you see how to solve for the m and b? Right? It's a linear system. Yeah, we can do this. I guess we subtract first from the second. Is that going to work? Yeah, that's the second equation here, right? I subtracted the first equation from the second equation, right? M plus b equals 3. I get 1m and no b's, right? So the slope is 1, and I can back solve and see that 2 is the answer. So the secret is 2. Yeah. Yeah, because I'm doing it mod sum prime, so I have to pick the prime. It's part of the scheme. So back when I picked the scheme, the secret is just a number from 1, 0 to the prime. That's what I think of the secret is. And again, these could be 100-digit numbers. This all works fairly efficiently on computers, right? Yeah. You mean reals? Yeah. No reals, please. I mean, I don't even know what a reel is, right? It's like this is like I understand a lot about what a mod is, right? I know how many bits I take to write it down, right? Like in a real, like even real number arithmetic in a computer is fake. It's something they do something bizarre. Yeah, it's also lots of things go wrong in real numbers or even integers, right? If you keep taking the square of integers, they get very big. If you mod them out, they do not. Right? So you're working all in the same system. Yeah. Because you give out some information when you give out the coefficient, maybe. Because it's not any d points. The coefficients, there's only d coefficients. He's asking, why don't I give out the coefficients? Because you don't, and how do you give out A0? You can't give out anybody A0. Right. So you give out d minus 1, and how do you ever give out enough? Right? You need to give out more packets than there are coefficients. Right? First of all. And second of all, it's not clear what information you're leaking there. Okay, so yeah. Yeah, they can guess the number, but what do you mean they can guess the secret, but they'll have no chance of getting it right other than guessing it without the other points, right? Because that's what I said, right? This is what this thing with the exclamation point. Okay, so this thing, right? Anyone, like if I tell them only 2 of the points, the secret can be anything. Okay, so they know nothing about it. So they can guess a point and they can fit a polynomial to it, so what? They haven't learned anything about the real secret. Does that make sense? Okay. Yeah. Anyway, so, okay. Yeah. Okay. Yeah. The secret helps. It makes it. It helps you because you only know the secret is between 0 and p, and that's fine. That's all you want to make. It's some number of bits. It could be any pattern in that bits. Okay. So so now we can do this for a quadratic too, right? This is how we do a secret, and it's nice, right? And this is something you did in middle school and probably high school and so on, right? A lot. You did a lot. Okay? So now what about a quadratic? Now it looks crazy, right? Because you have that x squared. Does x squared matter? Are we going to get linear equations still? Right, because when we plug in, the x squared will just be a number. Right? Look at this, right? This is the thing that often confuses students. It's like, well, how do you get linear equations? That's a quadratic. The quadratic, what we're doing is we're plugging in for the value of x. Right, to get this equation. So we plug in 1. What is 1 squared? It's 1. So we get a2. What is 1? a1 times 1, that's 1. And plus a0. And that equals 2, right? So the 1 here, this point, what it provided us was this 1. And we use that 1 to plug into this equation to get this set of this linear form. And then the right-hand side is 2, because that's what it's supposed to evaluate to. The polynomial goes through that point. At 1, it goes through 2. And the next one, we plug in 2, and then we see that 2 squared is 4, so I put that there. 2 is 2, and there's no x there, so that's fine. And the right-hand side is 4. Okay, and now I get 3, and now 3 squared is 9, and I accidentally put a 4. And but it's not really accidental, right? Why did I put a 4 instead of a 9? Mod 5, right? And so on. So now I have 3 equations and 3 unknowns, and what can we do? Well, we can just solve it, right? We can try to solve it. I'm adding the first and second there. We can, what did I do there? This is adding the first and second. Right? Because what happens is you get a 5a2, which is a 0. You get 3 a1s and 2 a0s, right? Does that make sense? And then 4 a1, I thought I put this in, but yeah, that I added the first and third. Okay, so if you add those up, again, you get a 5a2, a 4a1, and a 2a2. Okay, so now you can see here, you know you can get rid of the a2, right? You see the 2 a2s there? You just subtract. Okay? You get a1. And then you do some stuff. But this is where it gets interesting, right? So you multiply, when you plug back in, a1 is equal to 1. We didn't even need to do a division or multiply by the inverse, right? But at some point, what we're going to do now is we're going to subtract this, get a1, and we're going to plug a1 equals, we're going to solve the second equation here for a0. And that's what we're doing here. But I have a 2a0. So to get rid of the 2 from the a0, I need to multiply by the multiplicative inverse. This is where we use multiplicative inverses, right? When you solve linear equations, you do something called divide, or what they used to call divide, but we don't do that in this class. We multiply by the multiplicative inverse. I mean, later we will do divide when we get to probability, but not now. Okay? And so this is what you do, and you get this. Okay, and finally a2 you can back solve. Right, you've all done this. So the polynomial is now 2x squared plus 1x plus 4. What's the secret? What's the secret? Okay, excellent. So in general, given points x1 through xk, x1, y1 through xk, yk, we get something like this, right? Now, it's hard to look at. But it's a little scary. You see exponents. But this is not really a variable anymore, right? It's x1. It's some number raised to the kth power, and you can just evaluate it, right? And you produce an equation, a linear equation, on the unknowns. The unknowns here are the coefficients, right? Okay, so now I could produce how many equations? Well, there's k points So I could produce k equations, right? The right-hand sides are also numbers. I produce k equations and k unknowns, right? It's a linear system and k equations and k unknowns, right? So that means I can solve it, right? It's sort of getting to the right ballpark. But how do I know this will always work? Is it always true that if I have k equations and k unknowns that there's a solution? Right? There might be a solution, right? But remember, what's an example for two variables where there's two equations and two unknowns and there's no solution? Yeah.
You say x plus y equals 1 and then 2x plus 2y equals 2.
Well, there is a solution there. There's an infinite number of solutions there. 2x plus 2y equals 3. Yes. Yeah. But that's two equations and one unknown. You got 2 is not equal to 1. Yeah. Okay. Sorry. I mean, today I get, whatever. I'm sorry. Okay. So, but, this is like really beautiful stuff. And it's really just this, right? Really, this is the idea. But we don't know. The point is, there might be, another way to say it is they may not be linearly independent, right? The equations may not be linearly independent. The simple example for a line for two variables is two parallel lines, right? Two parallel lines do not intersect, right? There's no solution where both of those lines intersect. Okay? Does that make sense? Okay. Yeah. Oh my. Which one did I do? Here? Yeah, this equation. I took this equation and I subtracted it from this, right? Okay, so what I did is when you subtract the equations, you have a 2m here, and I subtract this equation, the first equation. I have 1m there. So how many m's do I have left? M. Oh, yeah, I have m, right? Okay. Now I also had a b here, and I subtracted a b here, so I have 0 b's. Okay, so I don't have anything there. And then I had a 4 here and a 3 here, and I had a 1. Okay? Okay, so good. Okay, so, we were here, we got this polynomial, we got these points, and now this is what I did twice, and it worked for me. And the question is, does it always work? Okay? Yeah. Okay. As long as the solution exists and it is unique, right? That's what I need to do. Okay? And this is what this fact tells me. There's exactly 1 degree d polynomial in this field that contains d plus 1 points. That's what it says. There's not 2 solutions. Like you could also have a system where there's many solutions, right? Like you have 2. That was your example, right? If you have 2 lines on top of each other. Okay, so you can have an infinite number of solutions. In that case, mod p, you would only have p solutions. But this is the fact that makes this solution work, right? Because we know that if we have the correct polynomial, this equation will be satisfied. And we know that there's only one. Okay? That's what the fact says. Okay? Okay, so there's another way to do this. Okay, so, but I haven't really proven the fact. So let me prove the fact by giving you another way to construct the polynomials. Okay? That hit all the points. Okay? Okay, so now, this is like, I have this poem about I love 0 and 1. This is a 0 and 1 thing. So, you see where the zeros are? Right? I'm going to construct a polynomial. Those are the points I want to hit. I want my polynomial to go through 3 at x equals 1. I want it to go through 4 at x equals 2. I want it to go through 0 at x equals 3. Right? Does that make sense? Okay, so now I'm going to try to find a polynomial that doesn't quite do that, but it goes through 1 at 1, and 0 at 2, and 0 at 3. Okay, let's just say I want to do that, because I'm just obsessed with 0 and 1. Okay, the y values are 0 at all the places but the first place, and 1 at the first place. Okay? How do I do that? Well, another thing with 0 is if I can get 0 somewhere. Let's look at this expression. X minus 2 has this property that if you put in 2 for x, it becomes 0. Right? So if you multiply 0 by anything, it's 0. Right? So that I know that this thing, if I just put in a factor of x minus 2, at 0, at 2, it will be 0. Okay? And I also put in a factor of x minus 3. And if I put in a factor of x minus 3, at 3, it will be 0. Now, everywhere else it will be non-zero. Right? Because we're doing mod p and there's inverses and everything. Right? If you multiply two numbers and you get 0, at least one of them was 0. Okay? So every other place other than 2 and 3, this is non-zero. Okay? Right? Isn't 0 awesome? It's awesome, right? It just stays around, right? You put a 0 here, you multiply it by something else, it becomes a 0. Always. Okay? So the value is 0 of this expression. The value is 0 at 2 and 3. The value is 2 at 1. So it doesn't quite fit what I promised. But it's not 1. That's from The Simpsons. That's a show that old people watch. I'm an old person. So divide by 2. But there's no such thing as dividing by 2. Mod 5, you multiply by the multiplicative inverse, which is 3. So that's delta 1. So now I built this polynomial that's 1 here, 0 here, and 0 here. Okay, so what should I do next? Well, I should build a polynomial that's 0 here, 1 here, and 0 there, right? So it's like the CRT. Okay? So it contains these 3 points. This one similarly is 1 here, 0 here, 1 here, and 0 here, right? And the way I did it is wherever I wanted a 0, I put in a factor of x minus that number. X minus 1 I wanted it to be 0, and x minus 3 I want it to be 0. So you multiply them together and you get something that's 0 in those two places. When you multiply them together, you get 4. So I need the inverse of 4, and you let's see what happens at 2. 2 times 1, 2, negative 1 times negative 1 is 5, is 1. Okay, and so on. Okay, so now I have 3 polynomials. What are the degrees of these polynomials? What's the degree of these polynomials? Well, let's look at the first one. X minus 2 times x minus 2. 3. What is the degree of this polynomial? If we multiply it out, what's the maximum degree? Does everybody see? 2. Yeah, thank you. I thought you sounded like Babak. So, okay, so now we're done, right? So we wanted a degree 2 polynomial, right? We're trying to reconstruct this, okay? And we wanted it to hit those 3 points, right? So I did this before using linear equations. Now I'm doing this sort of other weird thing, right? And now this is the polynomial that will go through those 3 points, right? So what happens here is that 3 times delta 1x, what is that going to do? Well, at 1, this evaluates to 3. Now at 1, delta 2 evaluates to 0, and delta 3 evaluates to 0. So this whole thing evaluates to 3. Right? Okay. At 2, delta 1 evaluates to 0. Delta 2 evaluates to 1 times 4 evaluates to 4, plus 0 times this thing, which will be 0. So you get 4. So you hit the second point as well. And the third point as well. The same argument. It's a 0 and 1 thing. Yeah. I didn't need delta 3 in this case, because I multiplied by 0. But if it was 3 commas 4, then this same construction works. It's probably a bad choice of points. Yeah. I couldn't hear you. You have to have at least 1, 1 all the time, right? That's what you're asking. Yeah. Well, because look at this argument, right? When I said I wanted this polynomial to be 3 at the point 1, okay? Now, this stuff, if they're not 0, there's a problem. I have to deal with the fact that they're not 0. But if they're 0, they're going to be 0. And I just have to deal with this one. Just multiply by 3. Okay, it's the same proof as the CRT. Remember I made the u be 1 in one place and 0 everywhere else? Which was only one other place, but yeah. Does that make sense? It's this property of 0 and 1. If this is 0, I don't care about it anymore. And at the point of interest, what I do is I make this polynomial. It's an awesome polynomial. It's 0 everywhere else. Okay? For all my other points, it's 0. For this point, it's 1. So now I can get whatever value I want here and not worry about the other guys, right? Because they're all 0 at this point. Right. No, that's right. Okay? And so now the question is, so I already I reconstructed the polynomial here. It's this one, right? So now the question, this way, just a second. This way I have this polynomial, and after a lot of calculations, I get the same thing. Okay? It works the same way. Yeah. Well, yeah. This one? Oh yeah, because, okay, look, what I want this to be is 1, right? It's x1 minus x minus 1, x minus 2, right? Now, I'm plugging in the value at 3. Okay, and I get a 3 minus 2 here, which is a 1, and I get a 3 minus 1, which is a 2. Now, if I multiply that all by a 3, I get a 6, which is 1 mod 5. So 3 is the multiplicative inverse of 2. That's what I did. Okay? Okay, yeah.
Still needed to know the coefficient 3.0 from the original points?
No, I didn't. I just needed the points.
Yeah, you needed those 3 points.
Yeah.
So, you could have just fit it normally.
How do you fit it normally?
Like, just solve the linear.
Yeah, so what did I do here? The linear equation, he's asking why didn't I use the linear equations? The reason I didn't use the linear equation, I gave you a new way to do it. What have I also shown? What have I also shown? Last time at the end, I said, yeah, there's these linear equations, but I said, well, is there a solution? So what have I done here? Good point. This is exactly the point. Okay? So in this case, I gave you 2 different ways to construct the solution, but one we didn't actually know if it worked. Right? But now we do. Right? And not only that, what I've proven is that for any d plus 1 points, there's a degree, any 3 points, there's a degree 2 polynomial that fits them. Because I've given you a construction. Okay? Flowers and grass, so nice. Okay, so what's a field? It's a set and 2 commutative operations, addition and multiplication, and it has all these things, and we can solve these equations, right? We use that in both places, reals, rationals, and complex numbers. The integers and matrices do not work. Okay? Integers do not have multiplicative inverses and stay enclosed. So what we do is we work with polynomials in this field, and that's addition works, but multiplicative inverses, that's because of the facts that we proved in the previous lectures, right? They have multiplicative inverses, and that's what I'm using. Okay, so let me give you a break, but you can have a break, but I'm going to tell you a story. Okay, but you can leave. It's not going to be on the test. Okay, so I grew up in Texas. I grew up in Texas, in a small town in Texas. I went to Cub Scouts in the trailer park. So that's where they were very nice to me for whatever reason, but that's the way it was, and so they had the population was generally like white or African American or Hispanic, and so they knew I wasn't any of those generally. So every once in a while, one of them would come up to me and say, "What are you?" And I'm like, "Well, I'm Indian." And they're like, "What tribe?" Sorry. I hope that doesn't offend anybody. But, all right. So that was a short story. Yeah. Where in Texas? Bryan College. My dad taught at College Station, Texas A&M, but Bryan was not. College Station is not a fancy college town. It's not Berkeley, and Bryan is not College Station. So yeah. Anyway, okay. So let's go on. So you had your break here. For a set of x values, x1 through d, xd plus 1, right? So what we're given is delta polynomials. What I wanted desperately was this delta polynomial. What I wanted to happen is that x equals xi. At the first point, it should be 1 for delta 1. And for all the other points, it should evaluate to 0. That's what I constructed. That's a delta polynomial. Delta means it's 1 here and 0 everywhere else. Now this one, if it's not one of the points we're talking about, we don't care what it is. I mean, it's not going to be 0, but we don't care what it is. What we care about is what is its value at x sub I, or if that's confusing or scary, just think of delta 1. At x equals x1, it should be 1, and everywhere else it should be 0. All the other points, it should evaluate to 0. That's what a delta polynomial is. Okay, given d plus 1 points, use delta I functions to go through the points. Okay, so I have these points, and now I have y values as well. There, I just had the points, and just with the x values, I can build delta polynomials. Delta 1 polynomial, delta 1 is 1 at x1, and 0 at x2, and 0 at x3, and 0 at x4, and so on. Okay, and now. Now, if you think about it, let's think of delta 1 of x. It's 0 at all the other points, but it's 1 at x1, right? That's what delta 1 is. So what is y1 times 1? What is y1 times 1? y1. So it says that if you multiply, the delta polynomial is 1 at x1, so y1 times 1 is going to be y1. So that's true. Will y2 times delta 2 contain x2, y2? It's the same argument, right? Now let's think about this one. Delta 1, y1 delta 1 times x plus y2 delta 2 times x. Does it contain x1, y1? Wait, we knew that y1 times delta 1x goes through this point, but now we're adding something. Why doesn't this mess us up? Because it's 0 at x1, right? That's what that says. It's like delta 2 is 1 at x2 and 0 at x1, right? And 0 at x3 and 0 at x4. So this doesn't mess us up, okay? And so yes, it contains that by the same idea. So you see the idea, right? So now, not only have we given you a method to construct the thing, we've given you a proof that there's a way to build polynomials that go through those d plus 1 points. Right? So this function contains all the points, right? All of these are 0 at x1. And so the value, when you evaluate this at x1, you get a 1 here, a 0, 0, 0, 0. So this goes away. And you get a 1 times y1, which is y1, which should be the value at x1. Okay? Okay. So now this is the proof. This is the proof. We want to prove this modular arithmetic fact. We want to say that given these points, there is a polynomial that goes through them all. And now it gets a little scary. But before, I didn't actually give you the polynomial here, right? I just said if they exist, then we're good. Okay? So what I did is, now this is hard to look at, but the numerator here is just saying, okay, I want this to be 0 everywhere else. So let's think about if I equals 1 here. What this would say is this is x minus x2 times x minus x3 times x minus x4 times x minus x5. So that product will be 0 at x2, it will be 0 at x3, it will be 0 at x4, right? Because every time, once you plug in that value into x minus x2, you get x2 minus x2, which is a 0 in the product, and so on. Okay? And now what is this term? There's no x in there. Those are all just numbers. So what I'm doing is I'm plugging in x1. Okay, so all I'm doing, this whole expression is exactly this expression with x1 plugged in, or xi plugged in. Okay? So what I'm doing is I'm making this whole thing 1. I'm taking this product, and then I'm plugging in x1 here, or xi if it's a delta I polynomial, and I'm multiplying by the inverse of the product, and I'll get 1. Right? So the numerator is 0 at all xj not equal to xi, because you have a product of x minus xj, and once you plug in xj, you get a 0 in that product, so you get a 0. And the denominator, this inverse here, makes it 1 at xi. I'm just dividing out this product when I plug in xi. Okay, and then this is the solution. So this is the proof that there's at least one polynomial. Okay? So you can solve it using a linear system, or you can solve it using Lagrange interpolation. It's called Lagrange interpolation. Okay? Okay. And it's the degree. Now the key here is the degree, right? So the degree here is you're multiplying together how many terms? One term for every other point. So there's d plus 1 point, so you're multiplying together d terms. Okay? So, and this is a degree d polynomial, and this is a degree d polynomial, and this is a degree. Now when you add them together, what's the degree? If you add together two quadratic polynomials, and one quadratic and one quadratic, you just add the coefficients of the quadratic, right? Still quadratic. Okay? So when you add degree d polynomials, you still get a degree d polynomial. Maybe a degree at most d. You could take the difference of the same polynomial and get a degree smaller. It becomes smaller. Okay? Okay, so the construction proves the existence of a polynomial. Okay, so this is proving this fact that I was crowing about at the very beginning of the lecture, after I restarted. Okay. Okay? Okay, here's an example. Degree 1 polynomial contains 1 and 3. You can work modulo 5. So you want to do this. We already did this example. X minus, so here what you need to do is you need to have a factor in for the other point, which is x minus 3. And I get an over x minus 3. What I'm doing now is I'm plugging in a 1. Right? I'm plugging in the x value of 1 for delta 1. Okay? So I'm going to get a 1 minus 3, which is a negative 2. That's so now I want to get multiplied by the inverse of that at 1. Right? I want to multiply by the inverse of negative 2, which is 2. Right? Negative 2 is 3 mod 5. So the inverse of 3 is 2. And I multiply out. Okay? So you can work mod 5. You can do the same thing. What you do is, for delta 1, I put in an x minus 2 and an x minus 3 factor. And then on the denominator, I plug in 1 for x here. I plug in 1 and get a 1 minus 2. And I plug in 1 for that guy and get a 1 minus 3. And that's what I get for my denominator. That's really not a denominator. Really, when something is in the bottom, you're multiplying by the multiplicative inverse. And then you get this. Okay? So this is how you just put them together. Okay? So you do this. The proof is that this numerator is 0 at all the other x values. And the denominator, you make it 1 by dividing up. Okay. Okay, so so I proved that there is a polynomial that will fit those points. Okay? But there could be many. Right? That's not all I need for the secret sharing. I want to show there's exactly one. Right? I want to show there's exactly one polynomial of degree d that fits those points. Right? Okay. Okay. So we're going to prove this. Any non-trivial degree d polynomial has at most d roots. Okay? A root is where a polynomial evaluates to 0. Okay, that's the roots fact. And I want to prove the uniqueness fact. Okay? So what is it? But let me just tell you what the roots fact is. A degree 1 polynomial is a line, right? How many times can it intersect 0? A line. How many times can it cross the x-axis? Right. The x-axis is where the value of the polynomial is 0, right? So how many times can a line cross the x-axis? Once, right? Remember this? Okay, a parabola can intersect it at most twice. That's what it's saying. But now we're doing this mod, so it's not clear the pictures make sense anymore. Okay? Okay. Now let's just assume the roots fact. I haven't proven it yet. I'll prove it in a moment. So we'll assume two different polynomials, q of x and p of x, hit the points. So it'll be a proof by contradiction. I'm going to take the roots fact as a fact. I'm going to prove the uniqueness fact. Okay, and this is a really standard trick, right? What I'm going to do next. Okay, I'm going to take two different polynomials, q of x and p of x, and I say they hit the same points. Okay, they hit d plus 1 points. They have those points in common, right? Okay, they go through those same d plus 1 points. Okay, now I think of this polynomial, r of x. Okay, now r of x is q of x minus p of x. Now, at x1, q of x equals p of x, right? So what is q of x1 minus p of x1? It's 0, right? What is q of x2 minus p of x2? 0. What is q of x3 minus p of x3? They have the same values on these points, right? 0. So how many zeros will this remainder polynomial have? D plus 1. Okay? If both of these points hit all d plus 1 points, then this difference polynomial has d plus 1 roots. Right? This r of x has d plus 1 roots and is degree d. Okay? Okay, do you see a contradiction here? Can I have a degree d polynomial that's... Well, I can. There's one degree d polynomial that I could have that has as many roots as you want. What is that? The 0 polynomial. So that says that this r of x is a 0 polynomial, the 0 function, which means these two polynomials are the same on every point. Okay? Okay, that's the contradiction of the roots fact, and that's it. Okay, so the trick here is to take these two polynomials and subtract them, really, and then use the roots fact. Okay? Okay, good. Okay, so now to finish, we have to prove the roots fact. Why is it that a polynomial has at most d roots? So again, intuitively, it's what you understand, right? Like if you see a line, it's only going to go through 0 once, at most once. It could be parallel to the x-axis, or a parabola. It can go through it at most twice, for the maybe above it, but in modular, I don't know what it looks like exactly. Okay, so that's what we want to prove. Okay, so let's remember something. Let's remember polynomial division. Who did that? You guys remember doing that in 10th grade? Didn't that suck? That was horrible. That was horrible. So we're gonna. It was terrible. Yeah. So okay, but this is how you do it. You can do it, right? So you just in my Emacs buffer. So you do x minus 3 dividing into this thing, right? Okay, so how do I do the division? What I do is I say, look, there's this 4x squared at the beginning, right? And there's an x minus 3, so I need to get the leading term right. So I put a 4x at the top, and I get a 4x times the whole x minus 3. And that gives me that. I'm taking it all mod 5, right? And so I get this expression when I multiply 4x times x minus 3. Okay? Then what do? I subtract, right? This is just long division. It's not really different than what you do with numbers, right? You get the leading digit right. Here you get the leading coefficient of the highest order term. And what you've done is you've gotten rid of the highest order term. Okay? So then you want to do this one, and then that's plus 4. Plus 4 will give you this result, right? Now it's gotten this leading digit right? The 4 is because you wanted to get a 4x here. And now you subtract, and you get that. Okay? So what you have is that when you divide x minus 4x squared minus 3x plus 2 by x minus 3, you get this 4x plus 4 plus this remainder 4. Right? What that means is I divided this expression by x minus 3. And I got this quotient. So when I multiply this together, I don't get that because when I get that minus this thing is 4. That's the remainder. Right? It's no different than long division with integers. Right? You get the quotient. If you divide by a number, you get the quotient times the original number plus the remainder. Right? So you get the quotient plus what you divide times what you divided by plus the remainder. Okay? So in general, if you divide p of x by x minus a, it gives some q of x and a remainder r. Okay? So it looks like that. Now think about it here. Let's think about this a little bit. P of x is degree d. What will this be? What degree will this be? Q. What is this degree? The whole degree has to be d. Right? So what is this guy's degree? D minus 1. Right? Does that make sense? When I write it out this way, the d minus 1, we're going for induction, right? We're going to do something with induction. We're going to prove there's at most d roots, and what we're going to do is we have this polynomial, we have this other polynomial with smaller degree. Okay? We have this annoying little remainder. Okay? Great. Okay. So here's the lemma. P of x has a root a if and only if p of x divided by x minus a has remainder 0. Okay? So p of x equals x minus a times q of x. Right? That's the lemma. It says if a is a root, this is actually, and here's the proof. So we know from before p of x equals x minus a times q of x plus r, right? Now, if a is a root, p of a is equal to 0, right? But if you look at this expression, p of a is equal to r, right? When you plug in a into that expression, you get an a minus a, which is a 0. 0 times q of x is 0, so what's left is r. So if you want p of a to be 0, it better be true that r is 0. Right? It's because we can do long division. Again, all that torture was so you could take 70, right? All that long division you did with polynomials. Okay? It's because we could do long division and write it like this x minus a q of x plus r, it becomes a triviality. Okay? So that's one. So if it has a root a, if this division has a remainder of 0. Okay. Now the second one is it's clear what we're going to do now here. What are we going to do? What's the proof? By induction. Okay? Right? We just did it for one, right? So what we say is, there's the base case or whatever, who cares? P of x is equal to x minus r1 q of x by lemma 1. Q of x has smaller degree, so you use the induction hypothesis. Multiply together. Right? That's it. Okay, so this says there's only one. Right? The roots fact, d plus 1 roots implies degree is at least d plus 1. Okay? So now it says, it says if you have d roots, I got to finish the roots fact, I apologize. If it has d roots, it looks like this. You can factor it like that. Okay? Now, if it has d plus 1 roots, it means you can factor it into d plus 1 terms. Now, if there's d plus 1 terms, what's the degree going to be? D plus 1. So that's a contradiction. So any degree d polynomial has at most d roots. Okay? Okay, so it works for all kinds of things. It doesn't work for things without multiplicative inverses, right? Again, you have to divide. Here, when we're doing this thing, what we're doing is multiplying by the multiplicative inverse to get this coefficient. Okay. So that was secret. It works in all these things. A field is a set with operations corresponding to addition, multiplication, and division. Okay, and so this is what we did. This is the scheme. Any k knows the secret. Okay, knowing k points, only one p of x. There's only one polynomial that goes through those k points. That's the whole point. So you can then evaluate p0. Any k minus 1, it could be any polynomial. Okay? Okay, good. Okay, so I'm going to skip this. I'll do this again next time. But let's end this. Let's look at this. Oh, yeah, look, I lost some packets. Oh, no, that sucks. Okay. Okay. So you have n packets in a channel that loses k packets. You must send n plus k packets. Any n packet should allow the reconstruction of an n packet message. So any endpoint values should allow the reconstruction of a degree n minus 1 polynomial. Actually, let me go back. I'll do this next time. But I do want to go over this. So first of all, why is this good? Why is this good? Why is this a really good scheme? Okay? So what we're doing is, what we have to do is pick a few things when we do the scheme. Just like with the RSA, we had to find a P and a Q and N and decide what our modulus was. So here, you have to choose a prime, and there's always a prime between N and 2N. So what it says is, say if I have B bits in my secret, okay, that means that the size of the number is 2 to the B. Okay? So it means my modulus better be bigger than 2 to the B. Right? Okay, so that's the first thing. So there's always a prime that's like within a factor of 2 of this number. Chebyshev said it. This is a poem. It's better than mine. Somebody else did it. Chebyshev was 20, and he proved this theorem, and then he went on and proved many more things. And the other mathematicians made up this poem. Anyway, working over numbers. So this rounding here says it's almost perfect, right? Because the number of bits we're working with in terms of our secret is exactly the number of, almost within 1 of the number of bits we're doing arithmetic over, and the number of bits of uncertainty, right? So it's totally perfect. The person doesn't know anything about what the real secret is, given the loss of 1 packet. Okay? And with k shares, you can reconstruct the polynomial. With k minus 1 shares, any of the p values are available for p0. Okay? Okay, so that's in any bit. So this is sort of an information theory argument, right? It says you know nothing about the value at 0, right? This is amazing, right? You can have all the shares, but 1 less of the shares than you need, and you know absolutely nothing about the value at 0. Okay? So you've got no information. Okay? Okay. So sounds good. Okay, so I'll see you on Thursday.